For this section, we will be developing the facade extents and panel frames as we explore lists and domains. So make sure you have Rhino and Grasshopper fired up. I'm going to enlarge my front view so I can have a bit more real estate to view geometry as we develop. First thing we're going to do is construct a rectangle. I know some of you might like to draw out the rectangle in Rhino, but I like to use a Grasshopper geometry to keep things a bit more parametric. The plane we'll be drawing this in is the XZ plane, given that we're looking at it from the front. And to set the dimension of this rectangle, which will be our facade boundary, we need a domain which defines the length and the height of this, or the width and the height of this rectangle. So we construct domain. And in case you don't know what that is, it's in math, and you click the domain. It is right here, construct domain. Well, you notice there's another construct domain, but a two-dimensional domain. I'll explain what these are. So a domain essentially is a numeric boundary. So a domain is defined by two numbers. So it can be from 0 to 1, or 100 to 200. Any two numbers can define a domain, and you see what we can start to do with domains as we go along. Okay, let me get rid of this. And by default, it goes from 0 to 1. But what we want is for it to go from 0 to any number we choose to set for the length. And the reason we want it to go from 0 is we want it to start from the origin, not -1 as it is by default, and 1. We want it from 1 to whatever. So we will use a number slider which goes from 0 to 100. Okay, and this gives us 0 to 35. But we want to feed in two values into this so that we can get two values out. So I'm going to use a merge and then copy this, feed one here, feed one here. This is how you make a list. Essentially, you have list 0 that has two items. One item at index 0 and index 1. The index is the address of an item in a list. We can have multiple lists that make up a data tree, but we will not be talking about data trees in this volume. In subsequent volumes, we will be addressing data trees. So just recognize that every item in a list has an address. So I'm going to put that away and get rid of that and connect this to here. So what is happening is, just to be more explicit, make this 0, connect it to here. Let's see what's coming out from here. Okay, so we have two domains, one defining the x and one defining the y, which is the height. So as we modify, you see those changes happen. But then how do we pass these two values into the x and the y? We do that by using the list item. I'm sure you're already aware with a list item, and this gives you pass in the list and you put in the index, the address of the item that you're looking for. That's a typical way to get the item out of the list. But Grasshopper allows us to explicitly get that by just clicking the plus sign, and no matter how you keep going, but you get to a certain point, it's ridiculous. So we just need the two values. We will connect that here, connect that here. So we can just make this a bit nicer. Okay, so we don't need this anymore. It's just a bit organized. Okay, now we see our rectangle. This is pretty much our facade. And the next thing we want to do, we want to divide this rectangle into a grid of rectangles that define the panel frames within this facade boundary. Okay, and to do that, this is where we use the two-dimensional domain. We're going to split this rectangle, which is a two-dimensional region, into a series of two-dimensional domains. And what I mean by that is, assuming we have this rectangle and we calculated from 0 to x as our first domain and 0 to y as our other domain, what we're trying to do essentially is generate a bunch of rectangles within this overall rectangle, right? So this is 1, this is 2, this is 3. But you notice along this domain, this domain is divided along here and along here. And so this particular sub rectangle is defined by a domain here and a domain here. This is why it's two-dimensional. It's not just one-dimensional along here. To do that, we would have to convert the rectangle to a surface. Okay, so Grasshopper already recognizes when you pass a rectangle or a curved geometry, a closed curved geometry into the surface node, it creates the surface. There are other explicit ways to create surfaces. Now that we have the surface, what we're going to do is divide domain, and we would connect this here. And remember, the U is the horizontal and the V is the vertical. That's an easy way to remember this. So the count is how many times do we want to divide along the U and how many times do we want to divide along the V. So what we will connect here is a slider that goes, we can do from 0 to 20. Connect that to U. Oops. Connect this to the V. Okay. Just move this about. And you notice what's coming out from here. It's a list of two-dimensional domains. So it's 1 point, so you notice the U and the V. So it goes from 0 to whatever, from 0 to whatever. And the next one is from this to this, from this to that. So question is, now that we have this list of segments, how do we use it to explicitly divide this surface? And that's where we use the isotrim. Even from the logo, you can start to see what it does. It needs a domain and it needs a surface. See how we split this up. I'm going to hide this surface. I'm going to hide this rectangle. Now we have our surfaces. Okay, so here's what I'm going to do. Let's visualize this list in this diagram that we have here. So I'm going to tag requires a location, so I'm going to get the area. Just going to connect this here, connect that to the location, connect this here. Let's make this small. Okay, then hide this. Maybe make this a little bit. Yeah, so this is telling us the domain of this sub-rectangle relative to the large rectangle. Okay, so I'm just gonna delete that. So we have our surface, and if you notice, as we adjust, this is the vertical. We should even name this vertical count. And horizontal count, just for consistency. We bring this here, and we can call this facade width, facade height. Okay, so that's great. We can control this, like that. So now how do we get our frame for this? I'm just going to extrapolate the edge of the individual surfaces, and just to show you, so these are individual surfaces. Yeah, so you see it's the list surfaces, right? Because of the list that came out from here. I'm going to use a curve. Again, just like we're able to construct the surface from the rectangle, we can get the defining surface, a defining edge from a curve. Then hide this. So now we have a list of curves. I'm going to hide the domain, the plane, XZ plane. We don't need to see that. Now we have our rectangle. So all we have to do is do an offset. I'm going to use the offset loose so that we can get a list of curves. Now if I use the other offset curve, which is typically what people use, notice that we get a different list structure. Alright, so it has pretty much created multiple lists with one item in each list. Now again, like I said, this is getting into data trees, so to prevent us from having to work with this, I'm using the loose offset curve loose. So we have a list of curves. What do we want the offset distance to be? Let's make that parametric. So say from 0 to 2. So it goes from 0 to 2. I'm going to put it here. but notice it offsets out. So what we want is to make this distance negative. So we can do negative, connect that there, voila. Or we can actually connect this directly, right click, expressions, and put -x. So we can reduce the number of nodes that we're using. So we have a list of curves here and a list of curves here. Is it possible to use this to define a surface within, so we can build out the frame? And we can do that with ruled surface. Ruled, there we go. Connect this curve, connect the curve. And now we have a surface. So hide this curve and this curve, and we notice that we have flat surface. I'm going to call this the frame thickness. Okay, just collect everything and put it here. So we can make adjustment to this, make adjustment to that. Neat. Gonna get rid of that. So what we also want to check is the indexing of this list. Okay, so I'm going to do an area. Let's see if this point match this, the lists in this structure in this surface. Okay, so let's get item, list item, like that, and the same thing we'll do for the centroid. Now we want to make sure that we have the same index value, so I'm going to do 100. Reduce that, connect it. So notice that this point has the same value as the surface. So we're dealing with a list that is organized. Okay. All right. So what we can do is now extrude, give it some thickness. So extrude, we're extruding this straight. I'm gonna go to perspective here. Remember when the X, Z, so that means we want to extrude in this direction, which is the Y. So I'm gonna do a Y. I'll connect that here. Alright, now we have some thickness. We give it a value of 0 to 8. Connect it there. Alright. Now, my unit is in feet. So to make sure I'm working with the right thing, I'm going to change this, divide this by 12. Connect this to my distance, so I can go a bit more. make this 12. Okay. I'm going to do the same thing, Control C, Control V here, so that we're working in inches as well. Okay. Frame depth, let's call it that. Maybe move all of that here. So we have all our parameters on one side. We can easily control what this thing is doing. Okay. That is, we have successfully completed our frames. But let's put a twist to this. Excuse me. What if we want the offset or the frame dimension qualities to change relative to a point? So any frame that is closest to a point, we want it to be large. So this is where now we're introducing attractor points.